ma'am.
Yeah. So, good afternoon to all of you. Once again, I would like to thanks to the organization committee who has given me this opportunity to present the talk in this faculty development program on fundamentals of polymer rheology and soft matter. So, the topic of my this talk is on the numerical simulation of complex fluids. So first, I would like to just show the how presentation will go. So this is the overview of whole the talk. I will introduce the complex fluids on which we are working, that is viscoplastic fluids, briefly, followed by the motivation, basically which motivated us to explore our research on this topic. Then I will briefly describe the research approach methodology to conduct the research on this topic. And finally, I will try to describe the findings in very explanatory way to you people, because you are from very diverse background, what I believe. So at least you can bring some message from this presentation or talk with you. So mostly my research findings I would like to represent with basic in different phenomena in heat transfer usually happens in different applications which we have observed in industries as well as in nature. So these are the forced convection, free convection and mixed convection phenomena. And finally, I would like to briefly describe where these results basically can fit in different applications, in real world applications. So let us start by introducing our viscoplastic fluid, which is called complex fluids. So what I can say to you is this is the type of fluid which is frequently encountered and experienced by you people in day-to-day life, nature and as well and industries. So what are these examples? Maybe food products, cosmetic products and hygiene like toothpaste, shaving creams, paints and mortar, what we are usually observed in construction sites. The waste disposal from industries, for example, mineral industries has a waste disposal of slurry. Largely utilized form solution in oil recovery from oil fields during fracking operations. And in nature, we are able to observe the flow of torrential lava, flow in avalanches and landslides, or mud flow in mountain streams. Now the question is, how can this fluid be so much distinguished from the classical materials, which we call solids and liquids? So the answer we can avail by doing some small exercise. So here we have three different materials in form of fluids. First one is fruit juice, second one is sugar syrup, and third one is tomato ketchup. And we almost all of us have experienced to feel how these fluids behave when we squeeze out or we pour from the bottle or pouch. So when we are talking about fruit juice, then what we can see? It immediately fills the glass, correct? When we are talking about sugar syrup, then what we can see? Yes, it will pour from the spoon or some pouch and it will fall on the surface, but it will not fill the whole vessel, whole bowl. And what about this third fluid? What we are calling it tomato ketchup. it will flow. It will fall on the surface, but it will form a little pile. So the question is, what makes them to behave so differently, and how we can characterize this behavior in general? So the answer is very much availed from the study of the rheology of such kind of fluids. Fine. And what rheology basically describes? Basically, it describes the deformation and behavior of the fluid. So here we have a relation of shear stress and shear rate, what mostly we have discussed in our first talk. But let me introduce the people who have joined freshly in this talk. So the relation between shear stress and shear rate, basically sufficient to describe this kind of behavior broadly. So here, what is this shear stress and what is this shear rate? So basically, this shear rate is observed in certain kind of processes. Like, for example, if we are mixing the fluid with some mixing hand, the speed which you are mixing, basically this fluid will experience shear rate under this action, or it is called the rate of deformation. And when we are talking about shear stress, then what is it? In more practical term, how much force you require to apply the given shear rate, that means to move the fluid, is called shear stress. And the ratio of this shear stress to shear rate will give us the viscosity. And what is viscosity? Viscosity is nothing but the resistance to flow. And when we are plotting this shear stress and shear rate on this plot, and if you are able to observe the relation between shear stress shear rate is linear direct proportion, then such kind of fluid are called Newtonian fluids, right? And here what we are able to see, the viscosity is constant. So here on the viscosity shear rate plot, you are able to see that viscosity of Newtonian fluids is constant. But such kind of fluids where we are able to observe the apparent viscosity, that means at each point on this curve, if you are moving, you are able to see the decrease or increase of this viscosity, then this behavior is not linear, shear stress and shear rate. So in that case, viscosity will either increase or either decrease, and such kind of fluids are called non-Newtonian fluids. So here whatever flow curves we have shown, basically we can characterize these fluids by power law fluids having two fitting parameters, consistency index and flow and power law index. Fine. Now coming back to the previous slide, what we have shown in the beginning. So in all these materials, what is so special? So let us take the again example of toothpaste. So when we squeeze a toothpaste, it flows like a liquid from the tube and spread over the toothbrush, where it will remain at rest till you will bring your brush up to the mouth. Then it largely deform once again due to the agitation and friction against your tooth. Let us take another example of this mortar. You had seen that on the construction site, this mortar is strongly mixed in the container. Then it spreads on the vertical wall to form a layer of couple of centimeter thick, which will remain rest from minutes to hour until it starts to rest. Let us take the example of one food product, mayonnaise. So when you see this mayonnaise, how it prepared, it basically prepared by strongly mixing in the vessel, and once it will prepare, you will take this mayonnaise and spread over the food surface. It will remain there at rest. So what is so differently behavior we can observe in these all materials? So we can say in other words, such materials behave as a solid when They are under the small shear stress values, but flow as an ordinary liquid equivalent to the Newtonian fluid once they will overcome this critical stress value. So this value which differentiate the behavior of fluid over the range of shear stress, it is called yield stress, and the material which follows such kind of behavior will fall under the category of viscoplastic fluids. And these viscoplastic fluids are also known as a yield stress fluids. So if you want to see the feature of this viscoplastic fluids, here we can describe more clearly on the shear stress and shear rate curve. So this is the Newtonian plot, but for Bingham plastic, you are able to see that this fluid will start moving once it will overcome certain stress value. And Bingham plastic fluids basically follow the linear relation between shear stress and shear rate. All viscoplastic fluids are not necessarily follow this shear stress and shear rate behavior linearly, but it could be non-linear also, similar to shear thinning and shear thickening. But my interest is basically in viscoplastic fluids. In our real life, we have example of such kind of material. For example, meat extract. It will start flowing only once it will overcome the stress value of 20 Pascal. Similarly, carbopool solution, it is also viscoplastic fluid, but it is basically following nonlinear behavior on the rheogram, and we are able to see that it will start moving until and unless it will overcome this much yield stress value. Now, if you see surrounding you, you have lot of material which have this kind of yield stress value, and here we have listed some typical yield stress values for common product, and you are able to see that the value of this yield stress varies from the order of 10 to the order of 10 to the power 2, from ketchup to hair gel. So now we can confidently say that what is this viscoplastic fluids and how this material behaves so differently, because we are able to see that this material basically has presence of some yield stress, which makes them different from the other classical material. And such kind of fluids basically shows dual kind of nature in the flow domain itself, having solid kind of behavior and having fluid kind of behavior. As a technologist, as an engineer, we always try to characterize this behavior mathematically, and here the simplest model proposed by Professor Eugene Bingham for such kind of fluid behavior by proposing this model. So what this model says? This model says that when the fluid experience the stress less than the yield stress value, it will not deform. That means no flow at all. And when it overcome this value, then we are able to see that this material will start flowing. Here I'm saying that it is not flowing. It doesn't mean that it is not flowing means stagnant. Here we are not able to see any deformation within the fluid. So just recall your toothpaste. If you press your tube, you are able to see the flow of that material out of tube. Correct? But that material is flowing like a plug. And we are not able to see any deformation in this fluid. It will remain as it is, it will rest on the toothbrush, but we are not able to see any kind of deformation. So what motivated me to conduct research in this viscoplastic fluid area? So basically, for my research originated from the various industrial applications where we are able to see the interaction of fluid and particles in different applications, where they will experience very complex geometries as well as very complex physical phenomena. So these are the few examples where we are able to see the fluid particle interaction or encounter of fluid with certain obstacle. So thermal treatment of various foodstuff. So you are able to see that in food industries, the food particles having different size and shape. See, it is ranging from 1 centimeter to micron maybe. So all these particles, all these chunks of fruit, they will send for the thermal treatment, and the media might be Newtonian or non-Newtonian. So here this solid objects will come in contact with the fluid media. Similarly, processing of granular particles, for example, polymeric material, they are made mostly in terms of violet and granulates. Pharmaceuticals also similar kind of particle system. Catalyst, what we are using in different chemical reactions, they are also having various shapes and size. If you see the stability of suspensions, then blood is also called one kind of suspension, red blood cell. So people who are working on this blood in different kind of sensor device or some kind of applications, they are they are able to see that this solid particles suspended in the fluid media. Even in pharmaceutical industries, we are able to see that many suspensions, they have micron size of particle present suspended in the media. If you see the nuclear and biological processes, they have also interaction of fluid and structure during the processing. Similarly, fermentation process, emulsion polymerization processes, we can encounter such kind of things. So if we zoom out in on the technological aspects of all these applications, what we are able to idealize. So you are able to see that the flow of viscoplastic fluids, basically when encountered any solid object in the way of its flow, and flow might be bounded or unbounded, then we can idealize this situation several ways. But where we can see such kind of encounter, for example, design of novel heat exchangers for complex fluids, thermal treatment of various foodstuff, flow dividers in polymeric processing applications. Here we have static mixtures where material is going to mixed by just passing through those obstructions. You can always observe this support structure of bridge when they will encounter the flow of very heavy mud or certain kind of very different kind of disaster happening. At that time, they will also encounter the flow of complex fluids past those structures. And of course, as a scientist, as a researcher, people always encouraged to conduct the research critically in such kind of encounter between particles and non-Newtonian media. So when we are talking about all these applications, we can always idealize this structure by considering ideal shape, sphere, hemisphere, spheroids, which can be suspended in the fluid media. And when we are talking about the flow of fluid past tube bundle heat exchangers, then they are structures like a very long structures in the flow path. For example, here you are able to see that these are the tube bundles having different kind of cross section of these tubes, and mostly fluid media will flow across this tube bundle, and you can see that they will experience different kind of obstructions in between their flowway, and they could be they are of different shape. Top of these things, also we can always feel that in the application of heat exchangers, boilers, there is a temperature difference between fluid and object. So when such kind of encounter happen, and when different kind of temperature conditions they will experience, then we can imagine different kind of heat transfer phenomena will take place. So what are these phenomena? Basically, they are forced convection, free convection, and mixed convection. So All these things motivated me a lot in order to conduct the research, particularly in the flow structure interaction in complex fluids. And here my interest is basically in long structures having different kind of cross sections. So these are the conventional shapes what we are finding in applications. But if you see this elliptical shape, then it has really very specific characteristics. This shape always found great attention in the industrial application because of two reasons. It offers a simple and conventional shape, that means free from singularity. We cannot see any kind of corner. And it covers the wide range of shapes, including very slender geometry to very blunt geometry and circular shape. So if you try to see these shapes, they are nothing but the variation in the major and minor axis of this cylinder, and they can cover the wide range of shapes in between these two extreme conditions. This very slender and blunt shapes can be also considered as a flat surfaces across the flow. So in order to understand the phenomena, forced convection, free convection, and mixed convection, when this kind of viscoplastic fluids encounter any structural hindrance in the path, then we can study more detailed way this kind of phenomena numerically. And let me briefly describe what are this forced convection, free convection, and mixed convection phenomena. So when we have fluid flowing past any object, and we have some external source to create the flow, then it is called the forced convection. What is free convection? When we have some temperature gradient between hot object and cold fluid, or hot fluid and cold object, then because of this temperature gradient, what happened? Temperature different density difference will happen, and because of this density difference, we are able to see the flow current will generate across this object, and we are able to see the flow which is called free convection. And if you combine this free convection and forced convection together, then we are able to see the mixed convection, where you have external mean to generate the flow. You have natural flow because of buoyancy difference in this flow media due to the temperature difference, and we are able to see the combination of force and free convection together. But here, when you look the direction of this flow, it will create different kind of condition in mixed convection itself. As we know, gravity is acting in the downward direction, so of course buoyancy will act in the opposite direction to the gravity. So when your flow is occurring in the opposite direction to the gravity, that is in the direction of buoyancy, what we can say, this flow current from external flow media which is coming, it will club up with the buoyancy generated flow, and it will aid this overall phenomena. So it is called the aiding buoyancy convection. But if your flow is coming in the direction of gravity, that is the outward direction, downward direction, and when it will opposite to the buoyancy force, then we can say that it is opposite effect, and we call it opposing buoyancy convection. And when the similar condition happen, where gravity is acting in downward direction, buoyancy acting in upward direction, and your flow is normal to this both direction, then it is called cross buoyancy convection. So we are trying to study the flow past the long object called cylinder and having shape of elliptical. When we keep this object in the path of the Bingham plastic fluid, and when we are considering the phenomena happening forced convection, free convection, and mixed convection, then what kind of results we are going to see. So mostly numerical methodology, what we are using, that is the finite element methodology. And ultimately the results what we are going to get, we are analyzed in terms of streamline isotherms. which are nothing but the mapping of your velocity and temperature in the flow field. Yielded and unyielded regions, this is the very specific characteristics belongs to the yield stress fluids, viscoplastic fluids, and how this yielded and unyielded regions modified according to this phenomena and shape of geometry we will try to study numerically. Drag coefficients are always important in various engineering application because it will count for the friction losses in the flow. So we can also analyze this drag coefficient because of this kind of phenomena. And finally, heat transfer coefficients are always interest in engineers because they want to make their process very efficient. So this is the overall methodology, but the people who are not aware of this numerical methodology, let me briefly describe what is it. So in general, if you see any fluid flow, we can always model this flow using certain conservation of law of conservation belongs to mass, momentum, and energy. So when we are talking about conservation of mass, it will give you equation of continuity. When you are talking about conservation of momentum, then it is nothing but the Newton's second law, and it is called momentum equation. And when you are talking about conservation of energy, it is nothing but the first law of thermodynamics, and it will give you the energy equation. So when you want to model the fluid flow, we are using all the laws from the physics, and this will give you the mathematical formulation of your fluid, how you are able to describe in terms of equations. And then we are trying to solve these equations mathematically in order to see how this fluid is going to flow. Similarly, if you want to analyze the temperature effect along
sir,
with the fluid flow,
benzene.
then you have to club up this energy equation along with your momentum equation. So when you are talking about this momentum, mass, and energy, you are able to apply all these equations to the systems which might be open or closed. And it is nothing. These are generally conservation equations. So what comes in must go out. And based on that, we have derived these equations which we are going to solve numerically. And these equations basically proposed in very long back by Navier and Stokes in very late 18th, 19th century. So what are these equations? Let me introduce. I really want to give you the feel what kind of equations basically represents your flow and heat transfer. So continuity equation basically nothing but the conservation of mass. Mass in is equal to mass out. There is a no accumulation. So we can write down this equation in terms of velocity vector. So velocity is a vector, so you are able to get this full form of the equation. What is this momentum equation? Momentum equation is basically the second law of Newton, and here momentum is nothing but the velocity into your mass. And here we are able to see that this quantity is tensorial. So velocity has three component, momentum has three component. So each momentum component has a direction x, y, and z. So you have one momentum equation resulting into set of three equation. What about energy equation? Temperature is a scalar quantity. Fine. And temperature is going to vary in x, y, and z direction. So we have this energy equation. Now, these equations are applicable to any kind of fluids. That means irrespective of any type of fluids, you are able to solve this equation. But what makes your equations very specific when you are using any typical fluids? This is the stress tensor, because this will take care of the constitutive relation between your shear stress and shear rate for any fluid. And when you plug your constitutive equation over here, you are able to see the application of your momentum equation, continuity equation, energy equation to the very specific kind of fluid. When you consider this term as a Newtonian fluid, then this equation is called Navier-Stokes equation. Here we are calling it Cauchy momentum equation because this is in the terms of tensor, shear stress, sorry. So when you solve these partial differential equations, and remember, all these equations are in form of partial derivative, so you need to have either write a code or you have to have very proficient commercial software which will solve these equations with lot of effort, numerical effort. So when you solve this all governing partial differential equations, what kind of problems you have? If you have velocity field, by solving this, by giving this velocity field to your equations, you are able to find out what are the pressure gradients prevailing in the field. If you have known geometry, if you have boundary conditions, if you have initial conditions, then you are able to get the velocity field, temperature field, and pressure field. So our research problems basically fall into the second category where we have geometry, we have very specific boundary conditions resemble to our problem statement, and ultimately what we are going to get, we are going to get velocity field, temperature field, and pressure field, and based on this resulting velocity, temperature, and pressure field, we are able to analyze what are the other gross entities we can derive from this solution, that is simulation. So these are the very typical kind of geometry we are going to consider in our research problem. So first one is forced convection with elliptical shape. Second one is the free convection, and third one is the mixed convection. So here object might be elliptical and cylinder and circular. So these are the long object in z direction. So this is your x direction, this is y direction. If you are considering the direction perpendicular to your screen, so if you will extend this object in that third direction, it will give you the long pipe having elliptical shape or circular shape, correct? And what we want to study, if this object we are able to maintain at some constant temperature or constant heat flux conditions which are frequently encountered in different applications, and if this viscoplastic fluid is going to flow across this long object, how our fluid and temperature field will experience this forced phenomena, natural convection phenomena, and mixed convection phenomena. So whatever the equations, mass, momentum, and energy we have to solve for in order to get this resulting quantities, we need to simplify our problem by considering certain assumptions and which are very much resemble to our problem statement. So what we are considering, our consideration for the problem is steady state flow, which is a laminar. Because object is very long in third direction, we can consider the gradient in that direction is 0, so we can consider two-dimensional problem. We are neglecting viscous dissipation due to our Brinkman number is very small in this case, and also we are considering all constant thermophysical property. What are these thermophysical property? This belongs to your fluid, specific heat, thermal conductivity, viscosity, all these properties we are considering constant, and this is reasonable, believe me. Why? Because we are considering the temperature difference between fluid and our geometry is such that we can consider all these properties are constant, and they are really constant if this temperature difference is small in reality. For free and mixed convection, we have to consider certain more assumptions which what we will discuss later on. Let me come to the governing equations. So these are the governing equations after imposing all these assumptions in simplified form. And these equations are in non-dimensional form. constitutive equation for Bingham plastic, we are going to plug in the momentum equation, and this constitutive equations are also in non-dimensional form. So according to the different kind of phenomena, forced, free and mixed, these constants differ according to the phenomena. And why this non-dimensional parameters we are observing here? Because when we are solving these equations in non-dimensional form, that means we are increasing the applicability of these results irrespective of the property of fluids, irrespective of the dimension of fluids. That means if you are considering very large range of Reynolds number, which is nothing but the rho u d upon mu, you are able to cover the Reynolds number. You are able to cover the dimensions, that is diameter of pipe, velocity, viscosity, all these parameters you are able to vary, and you are getting the Reynolds number range, and you are able to apply this results over the range of that parameter. Similarly, we are also interested in studying the orientation effect of this object when it will come across the flow of Bingham plastic fluids. These fluids doesn't have any boundary. They are flowing unboundedly. But if you confine the flow by placing this cylinder in between two parallel plates, that means in channel, then you can also observe what kind of different behavior this fluid will experience. So with this overall view of problem, let us start from the first problem, that is the force convection. So in force convection, what we are studying these long objects having different shape. Once they will come across the flow of this Bingham plastic fluids, then fluid is at some constant temperature, constant velocity, and object is at some higher temperature in the fluid. So you can see that this is nothing but the aspect ratio. It is the ratio of the axis of your elliptical shape. So minor axis to the major axis, for this shape we are considering aspect ratio. So when this E value is very small, then your object will have very slender shape. And when your E value is aspect ratio is greater than 1, then it has a very blunt shape. And if you have E value equal to 1, it will resemble to circular shape. So here we have assumptions of flow considering steady state and laminar, two-dimensional, constant thermophysical property, and no viscous dissipation. And continuity momentum equations we are able to see here by using this scaling variable to making velocity, length, pressure, shear stress, shear rate non-dimensionalized along with the temperature. And ultimately, when you are using these scaling variables, your governing parameters which evolved in these equations, they are Reynolds number, Bingham number, and Prandtl number. So basically, Reynolds number is nothing but the ratio of inertial flow to inertial uh, forces to viscous forces. Bingham number is the ratio of yield stress to viscous stress, and Prandtl number is the momentum diffusivity to thermal diffusivity. Now, when we are talking about this flow condition, then what kind of flow condition we have assumed? We have assumed this object came across the path of fluid, but none of the any boundary disturb this flow condition. So it is basically considered as a unconfined flow. So in order to consider unconfined flow, then the flow has to be very large, and we have to impose the boundary condition at the inlet inflow, at the outlet outflow, and at the middle plane we are imposing symmetry. Why symmetry? Because we are considering steady state laminar flow, and whatever the ranges of this parameter Reynolds, Bingham and Prandtl we are considering for our study, over this range of parameter our flow will be symmetry. So whatever you are able to see on the upper half, same phenomena you are able to observe in the lower half. So what are the numerical parameters we are going to solve? So first one is Reynolds number, second one is Bingham number, and third one is the Prandtl number. So range of this parameter we have chosen such that they are really encountered in various industrial applications. Prandtl number 1 to 100, these are the Prandtl number frequently encountered by different media, fluid media in the applications. Aspect ratio we have covered from very blunt shape to very slender shape, having 7 values. Now, what about domain and grid? Because you are solving mathematically our equations, so you need to have certain mathematical numerical parameters you have to choose. So when you confine your geometry with certain domain, then you need to confirm that this domain doesn't have any effect on the result, and for that we have chosen our domain very large, sufficiently large to consider the unconfined condition. What about grid? In order to discretize this flow domain, we need to generate the grid, and these grids are also considered as a numerical parameter, and we need to optimize this grid inside this domain. Now, the size of domain and the number of grids we have to optimize because we are solving numerically, correct? So we cannot consider very huge domain which will really resemble the unconfined condition, because the moment you are making domain larger and larger, you are putting lot computational effort to solve that set of equations. Similarly, if you are discretizing the domain more and more number, you are putting more effort, computational effort to solve the problem. So we need to optimize this numerical parameter by conducting certain tests, and we have to optimize by giving certain values. Finally, the discretization of this domain has very much effect on the results. So we need to first make sure that the grid should not affect the results. So for that we need to conduct the grid test and domain test, and we have to choose appropriate shape and size of the grids. Also, you are able to see that the grids are very fine on the surface of the geometry. While you are going away from the geometry, your grids are become much more coarse. Basically, the temperature gradient and velocity gradients are very steep next to the solid boundaries. So we need to make this grid very fine in order to capture those changes. While you are go away from the geometry, your velocity gradients are not that much steep because they are just coming out of the thickness of the boundary layers, momentum and thermal boundary layers. So after doing all this exercise, we have to come up with very specific choice which resemble to Bingham plastic fluids. So why people are saying this Bingham plastic model, if you want to solve, then it is challenging. That is a reason. Fine. So let me show you what is the actual reason. First reason is what? We are able to observe the flow in terms of solid-like region and fluid-like regime based on the stress distribution in your flow domain. So here let me explain you this simple statement by considering our flow in the pipe. So when you have laminar flow in your pipe, and particularly it is Newtonian fluid, we all are aware of one fact. The maximum velocity we are going to get at the center of the pipe, and which is twice the average velocity. But when you are observing the velocity profile for your viscoplastic fluids in the same channel, same pipe, what you are able to see that at the center, in this central region, we are not able to see any parabolic shape, but it will become very flat. So what is the meaning of this velocity profile? So let me explain you. In this central region, your fluid is moving. All the elements of fluid will move with the constant velocity. So you are not able to see that the layer which is moving up upside to this layer having some different velocity. They are moving with same velocity. So in general, we are able to see that in this region, velocity gradient is zero. But still, it is moving with some constant velocity. Now you are able to understand why your toothpaste will move like a plug. So you can exactly think about this central region like your toothpaste, how it is coming out from the tube. But when you are moving towards the solid boundary, because of the presence of this boundary and the boundary condition, which is nothing but the no slip condition, velocity is zero, what we are able to see that the velocity will vary from velocity in the plug zone to the velocity zero. So there is a temperature gradient. So here we are able to see the deformation. That means velocity gradient exists. And this is the image of the mud flow in the open channel. And if you see carefully in this image, what we are able to see that there is a some boundary which is making this plug-like region different from the region which is next to the wall. So in reality, this fluid is moving with two kind of characteristic. One is like a solid, one is like a fluid. Correct? Because this is the characteristic of solid, where we are not able to see any velocity gradient. Correct? So when I'm writing down this Bingham plastic model in terms of viscosity, then viscosity will become infinite. Why? I told you when tau is when your stress is less than yield stress, your shear rate is zero. So what is viscosity? Viscosity is shear stress upon shear rate. So in denominator, your shear rate is zero, then viscosity will become infinite. So this is the point where we are facing challenge numerically solving this Bingham plastic fluid. Why? Because numerically we are not able to solve infinite. It will give us numerical error. So how, if you want to solve this Bingham plastic behavior, then what are the possibilities? So we have overcome this hurdle by doing some modification in the ideal Bingham plastic model. So this is the ideal Bingham model. What it says that when your stress value is less than yield stress, viscosity is infinite. That means very high. But when your stress value is less than yield stress, it has a reasonable viscosity like a Newtonian fluid. So if I will modify my Bingham plastic model such that my viscosity will become very high, not infinity, but very high when my stress is below yield stress. And when this stress value is high, my viscosity will become like a Newtonian, then it is enough for me to solve this problem. So this is the Papanastasiou model where we have multiply our this term with bracket. This is called the exponential growth rate term. So here we have one more parameter m. So if you see this carefully m, and if you think that this m is very high value, then what happened? This second term will become 0, right? Correct? When your m will become very high, then your exponent term will become 0, and it will give us viscosity resemble to this. So here in biviscosity model, we have another parameter. We have model by substituting this bracket where we have ratio of yield stress viscosity to the Bingham plastic viscosity. And when this ratio will become very high, then it will approaches to the ideal Bingham model. And in Berkowitz model, we have modified the strain rate, that is the rate of deformation, by delta. And when this delta value is very small, you are able to see that it will approaches the exact Bingham model. So here we have schematically represent this model. So your exact Bingham model is what? It is a straight line passing through the yield stress value. And what is your Papanescu model? You can see that at low stress, low strain rate value, it has a very steep curve, steep slope. So this steep slope resembles to very high viscosity. So at lower value of shear rate, your viscosity is very high. But once it will go at the above this values, you are able to see that it will smoothly give you the constant viscosity. So we are replacing our ideal Bingham model using this modified model, and we try to see how our results will come. So this M value, we have to choose arbitrary, and we have to see what are the effect of this chosen value on the yielded and yielded surface. So this white color is like a fluid like regime, and this is the solid like regime. So here your stress value fall below the yield stress, and here your stress value is reasonably high where you are able to see that fluid is flowing like a Newtonian fluid. So after choosing our parameter for the constitutive model, we are able to solve this set of equations, and then we are able to see the results. So first result, that is the streamline pattern. So as an engineer, we are always interested how vortex are forming. Why we are interested in formation vortex? Because this is the region where we are able to see that efficient heat transfer because of turbulence, and efficient mass transfer if mass is transferring from solid geometry to fluid in case, and we can always see that there is a mixing happen properly. So here you are able to see that the object is very much blunt, the formation of vertex is larger. But the moment your object is becoming slender and slender, we are able to see that over the same range of parameter, we are not able to see any flow separation. So we are able to see the effect of all these parameters on this vertex length, and which will be useful when you are designing any operation where you need efficient heat transfer and mass transfer and mixing. Similarly, we are able to see that as the Bingham number increases, the size of this vortex basically decreases. So Bingham number is nothing but the increase of yield stress. So if your fluid has higher and higher yield stress, that means that inertial force is not sufficient to overcome the yield stress, and basically it will behave like a solid like material. So here we have a analysis of this Bingham number value above which we are not able to see any wave formation or vortex formation. So this is the range below which you are able to see efficient mass transfer, heat transfer, because vortex is forming, and you are able to see there is a mixing is also sufficient in case you have such kind of requirement in your application. Now coming to the shape of the yielded and unyielded surfaces or zone. So here we are able to see that when your shape is really circular, your zones surrounding this geometry will be divided into 1, 2, and 3 different shapes of zone. These are the unyielded material, that is unyielded means solid like, yielded means liquid like. So this solid like material will remain on the surface of the geometry. These are the solid chunks which will suspended in the fluid regime, and this is the material which is moving like your toothpaste plug when it come in this region. So important thing is what? When we are changing the shape of our geometry, these shapes are reasonably changed. Correct. And you are able to see that at the back side there is a formation of this stagnant unyielded material is more for the slender geometry, and when you are making your shape slender, then you are able to see that there is a disappearance of that material which stick to your geometry. We have always analysis in terms of how this stagnant zone will vary on the range of the parameter. Correct. Now coming to the drag coefficient. What is this drag coefficient? Drag coefficient is nothing but the force exerted by your fluid in the direction of the flow due to this geometry. So here we are able to see that the drag basically decreases as the Reynolds number increases, and you can see that as Reynolds number increases from here to here, your drag value dropping down. But on the other hand, you are able to see that over the same value of Reynolds number, if Bingham number is increasing, then drag is increases. So basically these parameters will play a role in terms of this drag. Where we are able to see this application of drag, when you are trying to design any process, you are always interested how much friction is going to experience in that whole system because of this solid objects once it will come across the flow path. So here we have a range of Reynolds number, we have a range of Bingham number, and we have a range of our shape of the geometry. Correct. And we have specified this range in very beginning, and we have this results for particular values what we have solved in our numerical problem. So in order to make this problem more universal, what we did, we proposed the correlation for drag coefficients. So people can extract any value in between the range of our results in their applications. Now coming to the heat transfer part. So here what are these? These are the isotherm patterns. So basically these isotherms patterns are nothing but this is the mapping of temperature in the fluid domain. And in force convection, your momentum is completely, flow is completely different from the heat transfer. So you can independently solve flow and heat phenomena separately. So here we are able to see that at the low value of your Prandtl number and low value of Reynolds number, most of the heat is transferred by conduction. Why? Because these isotherms are making very circular kind of pattern next to your hot body. So here by looking this pattern, you can visualize that there is a heat transfer is happening, but it is because of not advection, that is because of not flow, because flow is very slow, and because of this less inertia, most of the heat will transfer by diffusion. But when your Reynolds number will increase and you are able to see that at high Reynolds number, we have a flow separation and we have a vertex formation. So at the rear side of this geometry, you are able to see that the distortion of these isotherms. So which indicates that there is a vertex formation, and as your flow increase, you are able to see that boundary layer and thermal layer both are decreasing and heat transfer will become much more faster. You can see the shape of this isotherms for low Reynolds number will not much different for different shape of geometry, but at the high Reynolds number you are able to see that the shape of this isotherms will modulated because of the presence of the different shape of geometry. So you can see that this slender geometry and this circular geometry has different kind of isotherms pattern at high Reynolds number. If you will move from circular shape to more blunt geometry, then you are able to see that at this shape, because of very streamlined flow pattern, very thin thermal boundary layer, we are able to see. So ultimately, what is our aim? We need to find out what is the heat transfer coefficient, fine, and which will basically used in different kind of heat exchanger boilers. When they are designing, you need to have this kind of correlation for the range of parameter. So we have proposed the heat transfer coefficient correlation in terms of Colburn factor over the range of our parameters which are in our interest. Now, if you see the shape of this geometry will become little bit tilted, then you are able to see that this flow is no more symmetric. When you have vertical orientation, you are able to see that exactly whatever happening on upper half, that will exactly happen in the lower half. But here, if you tilt the geometry, you are losing the symmetry. So we need to solve this problem in full domain. And in force convection, along with the same kind of boundary conditions, so I'm not describing more, the range of parameters are almost same, where we are considering our flow is steady, laminar, and when we are choosing our numerical parameter appropriately for this problem, let me take you directly to cells. So here you are able to see that the flow patterns, very nice flow patterns you are able to observe because of the orientation of your object. And the moment your object will become very much blunt, slender, then you are able to see that this vortex formation will gradually disappear. And similarly, if you see the yielded and yielded region, again, they will modulate the shape of your yielded and unyielded region next to your geometry too much because of the orientation. Now, let me explain one more thing at this point. When we have this yielded and unyielded region, what is the importance by observing this thing? So when we are considering some temperature sensitive material, for example, pharmaceutical or food product, where you are able to see that if your material is very much stagnant, then you are able to see that there is a growth of bacteria happens in that biological or pharmaceutical product. Or sometimes we are able to see that because of this material where we are not able to see any kind of velocity gradient, there is a no mixing happen, or mixing is very slow because of diffusion only. So such kind of yielded and yielded zones basically gives us idea how our mass transfer, heat transfer will affect because of the presence of this such kind of variation in the zones. Ultimately, if you see the drag for such kind of slant oriented geometry, we are including one more component, that is the lift coefficient, because of the loss of the symmetricity in the flow, and we are able to correlate this data over the range of parameters. These are the isotherms pattern, which are really very much different from the regular shape. For constant wall temperature and constant heat flux, these are the boundary conditions which we have imposed on the geometry surface, and you are able to see that heat transfer patterns are very much different for your constant wall temperature and constant heat flux temperature. So basically constant wall temperature we are observing when heating and boiling process are happening, boiling and condensation process. So for example, inside your tube there is a steam, then you can consider this at a constant wall temperature. But if you have applied some power heating element on the surface of the tube, for example some heating coil, then we are considering it is a constant heat flux condition. So temperature sensors are similar kind of long element inserted in the fluid. So you can always consider if your fluid media is non-Newtonian and these elements are long cylindrical object having some constant temperature or constant heat flux condition, then you are able to see that how this kind of objects will affect the flow pattern and temperature thermal pattern in the flow. And finally, we propose the average Nusselt number for this kind of orientation, different orientation over the range of parameter. Now coming to the free convection. In free convection, mostly what we are observing one thing. This flow is not happen because of the external force. This flow is going to happen because of the temperature difference prevailing in this fluid domain. So as your geometry is at high temperature and fluid is at lower temperature, because of this temperature gradient, density will change from high temperature to lower temperature, and because of this temperature difference, there is a flow current will generate next to this geometry. So here in your momentum equation, we have to incorporate this body force, and this body force will take care of this variation of density with temperature. So this is called Bolzinansky approximation, and we are knowing that this bouncy force is acting only in y direction. So this term will appear in the equation in y component, and the limitation of this equation is what? This approximation is applicable over the narrow range of temperature difference. For large range of temperature difference, we cannot say that density is linearly vary with temperature. So with these assumptions, we are solving our equations for natural convection or free convection phenomena. But one more thing I want to emphasize here. Here your temperature term, the zeta is nothing but non-dimensional temperature. This temperature term is coming in the momentum equation. That means these two equations, energy and momentum, are coupled. So in this case, whatever energy equation is there, it will definitely affect the momentum transfer, because there is a temperature difference prevailing in the domain and which will affect your density, and because of this density difference, flow is happening. So now let us see how our results will affect because of this phenomena. So here I really want to tell you one thing. Because we are interested in finding out yielded and unyielded shape in the domain, here our these shapes are definitely affected by the energy term, temperature term, because it will affect the flow equations. So these are the governing parameters: Bingham number, Prandtl number, and Rayleigh number. So Rayleigh number is basically taking care of our free convection phenomena. This Rayleigh number is the multiplication of the Grashof number and Prandtl number. So these are the parameters, these are the grids, and here we are able to see that your patterns of yielded and unyielded regions are very much different compared to the forced convection. And we are able to see that this all these patterns are very much affected by the shape if you are changing the shape from 2 extreme, 0.1 to 10. So here you can see that the flow pattern and temperature isotherms on the other side of the geometry, and we are able to see that as the Bingham number increases, these flow patterns will become very much symmetry to the geometry, and we are able to see that isotherms are very much symmetry to the geometry. So here we are able to see that as the Bingham number increases, most of the heat transfer is going to happen by conduction. This is what my isotherms and flow pattern tell me at this time. So let me take you to the yielded and unyielded region. So whatever results we have shown in the isotherms and streamline, we are able to relate with yielded and unyielded region. So as the Bingham number increases, we are able to see that all the fluids around surrounding this geometry will freeze, and we are not able to see any kind of movement in the this domain, and most of the heat will transfer in this fluid like a conduction. So in order to process such kind of material in convective zone, we need to operate our whole system at lower value of Bingham number, otherwise all the material will freeze above certain Bingham number value. Similarly, you can see that the shape, how it will modulate the yielded and unyielded region. We are able to see that at high Rayleigh number, where your convection is buoyancy effect is much more, you are able to see that this fluid regime will prevail up to the higher value of Bingham number. That means you need more higher Bingham number to see the freezing kind of material characteristic to the geometry. So we can here also we are able to correlate the data, and we are able to propose the correlation for the Nusselt number over the range of parameter. And here, what is this NUC? NUC is nothing but the conduction limit. So you can see that as Bingham number increases, we are not able to see the change of any Nusselt number value over the range of E. So this is basically conduction limit, where heat transfer is mostly happen by the conduction. Now coming to the mixed convection quickly. So in mixed convection, we have flow as well as we have our natural convection happening because of this temperature difference. So we are going to club up both the phenomena together for the mixed convection, and we are able to see the results very quickly after looking this choice of parameters. You can see that here your flow patterns are very much similar to the forced convection, correct? But the beauty is what, if Bingham number increases, if your Rayleigh number also increases, that means when Rayleigh number increases, your free convection contribution is increases, then most of the results will fall in the same category. That means you are able to see the constant yielded unyielded region over the range of parameters. And here we are able to propose this Nusselt number in terms of forced convection and free convection, which is basically cover the large range of parameters. Finally, briefly, I want to show you, if you will confine your flow by imposing two solid boundaries, then what kind of changes you are able to see in your results. So here you are able to see that if you will bound your flow with two solid boundaries, then you are able to see that there is a very steep shear rate you are going to observe. These are the high value of shear rate next to the wall, next to the geometry. And where shear rate is high, you are not able to see any unyielded like solid like region, so you can see that. But where your shear rate falls below certain value, then you are able to see that your material is going to start freezing. But you are able to convince yourself at this point, this yielded unyielded flow pattern is very much different from mixed convection what we had seen in unconfined condition. These are the effect of shapes, and you can see that the shape has a reasonable effect at high Bingham number. And these are the isotherms and streamlines. These are the average Nusselt numbers what we have plotted just to show how they are going to change over the range of parameters. But ultimate goal is in to correlate in terms of correlation. So this is the correlation we have derived for the range of parameters, broad range of parameters, and many number of parameters, which is applicable in many applications. So with this findings, let me take you to briefly description where we can see the application of this kind of research. So we are able to see the processed food in market, and you are able to see that fruits and vegetables, they are preserved for a longer time and they are selling in the market. So when you are treating these fruits, particles or vegetable or cuttings of your fruits, then you can consider your system having particles along with the fluids. And the moment your fluid and particle combine in the system, you are able to see the complex phenomena. And during your processing, they are experiencing convection, conduction together, and depend on the shape and size of the material, they are going to show the different kind of behavior. And if you want to understand all these findings by conducting experiments, then it is really lot of trials. You have to conduct lot of laboratory experiments, which are really very much difficult to conduct at certain level. So what is necessary thing? To increase the shelf life of this material, you have to have designed the efficient thermal processes along with the optimization of energy and food quality. So this is must for any product. So in order to derive the conclusion on your shelf life of material, instead of conducting experiments a lot, you have always support of experiment to your numerical findings, and it will make your life easy. It will give industries lot of relaxation in conducting such kind of experiments and research. But yes, we have to always remember when you are using your numerical data to any system or to analyze any system, we have to keep in mind what are the limitations of our numerical findings. Basically, these numerical findings applicable over the range of parameters what you have considered in the study. Beyond this range, these findings are not that much applicable. The assumptions in the study what you are considering, these are the limitations to your study because you are simplifying by relaxing that small phenomena you are assuming your system will behave like this, but if you are considering that phenomena has much more contribution in your process, then you cannot consider that assumption, you cannot consider that findings. And on the other hand, when you want to relax all the assumptions, it is very difficult to solve the problem. So what we used to do, mostly whenever you have any problem, you have to analyze what kind of phenomena is dominating on the others. So it is very much um, acceptable if you are considering the dominating phenomena and you are neglecting other phenomena. Because of this dominating phenomena, your system is really applicable to the resemble to the actual system. We really need to validate the model through the experimental test or other simplified systems results which are available in the publication or in literature. Whatever input parameters you are using, for example, viscosity, density, specific heat, thermal conductivity, these are fully weighted before the utilization in the numerical simulation. So with this concluding slide, I would like to say thank you to you uh, to be present in this presentation. So I'm happy to answer if you people have any question related this work.
Yeah. So the session is now open for questions. I'm thinking there are a lot of questions from participants side.
Uh-huh.
Yeah. So questions. Yes, you can unmute your mic and can ask the question. Hello.
Hello.
Yeah. Is there any question? Okay. After lunch, they are getting.
Yeah. I had that feeling because this is like very theoretical and numerical work. People might not have that much um, enthusiasm. I can
But
understand this.
in the morning we had a yoga session. Then at that time, everyone was very much enthusiastic. Akshay, do you have any question?
It's okay.
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 Yeah.
Yeah.
Uh,
Mm.
so, ma'am, you have described whole lot of things: continuity equation, constitutive equations, effect of shapes, and you have also nicely explained the applications of numerical simulations to complex fluids for designing the efficient thermal processes and optimization of food quality product. So with this, I would like to thank you, ma'am, on behalf of University Institute of Chemical Technology, Kavaitri Bahinabai Chaudhary, North Maharashtra University, Jalgaon, and hope that you can also provide the same assistant in future if we organize such a type of workshops. Thank you very much, ma'am.
Yeah. Thank you so much for giving me this opportunity. It is my pleasure, and I'm very much happy in future to get such kind of opportunities
Yeah,
whenever it will be there. Thank you so much.
yeah. Thank you very much, ma'am. So I think all of you are here. So Can I discuss some points with you?
Yes, sir.
Okay. Uh, just a minute. We have a time, lot of time, so I'm going to mute this